far as the modeling goes, as using solver on it, products mix is the only kind of problem that we've even used, because that's what the tennis racket problem was. It was product mix. We weren't really specifically thinking of what type of problem it was, because we were going through iterations of learning solver and how solver works. And so we didn't really worry about the fact that it was product mix and all that implied. But then as soon as we shifted over to do what they do in chapter 3, when we looked at that, oh, wait a minute, okay, let me, too many things in my mind at one time. So we did shift over and we were looking at small product mix problems last time. We'll look at that in just a minute. It was the color and black and white t-shirt thing. And it was small because what we wanted to recognize that it's not just what's the best mix of products, but also that you would be looking at sensitivity analysis after the fact of saying, is this the, what if something about this changed? Well, here's the situation though. Once you have a solver model going and you want to make a change, a lot of times the change you want to make is to the constraint value. So if you change a constraint value, it has no immediate impact on your output. The only way you see the impact on your output is if you go ahead and run solver again. And so for us just to try to make a one-way table or two-way table, just to make a regular data table didn't really help us. And so we discovered there was another tool, solver table, that would allow you to do what needed to be done. And here's what needed to be done. When you changed an input, like a constraint value, when you changed that input, you needed to run solver again and then look at how that impacted the output. Change the input again, run solver, look at the output. Input, run solver. Okay, so that is accomplished not through a regular data table, but through a solver table, which was written by the authors of our textbook. What we discovered last Thursday, and kind of began to figure this out in my 10 o'clock class, is that solver table wasn't working on Macs unless you were running Parallels Bootcamp something that allowed you to run the Windows version. And I don't know that that has always been the case. I kind of don't think that was always the case, but it seems to be now. When Apple does stuff that updates things, it changes how these things interact with it, and it appears now that is. Anybody using a Mac that can do this without running Parallels or Bootcamp and running the Windows version? Okay, then that's pretty much the conclusion I've drawn now. This happened a couple of years ago with Palisade. Mac users used to be able to, while running under the Windows version, could run the Palisade tools. And then a couple of years ago, there was some change that was made with the Apples, and the reason I knew is because people whose computers had updated and people whose computers had not updated, some were able to still run Palisade and some were not. And since then, really, no one's been able to run Palisade on the Mac since then, even with the Parallels and Bootcamp. Well, so we'll cross that bridge when we get to it in the last 2 weeks of the semester. But for now, you will have to, to be able to use it in class and work along. And we use solver table all semester, so you'll need to get that, get it where you can run the Windows version, whichever you choose. So when we went through this PowerPoint, this is the same PowerPoint we brought last time. When we went through this, we reiterated some of the things that we had really discussed when we were doing the tennis racket example to learn solver. Then we went into this itty-bitty problem on color and black and white shirts, and the reason it was so very small was so that the concepts would be very intuitive, particularly when we were learning solver table. So that when we were learning solver table, the things that we could see out of the results of that would be so much clearer and easier to understand because the model was so small. So we put the model together, which took no time at all, and then we did learn about solver table here with the one-way and the two-way solver table, where we were varying the time available to us on the machines. And then the next one, both the time and the cache that were available. Okay. And so we looked at that, and then we moved to example 2. No, we didn't move to example 2. Now we're going to move to example 2. And example 2 is less conventional than what we think of as a normal product mix. Because when you think about a normal product mix problem, it's you trying to produce the products that will make you the most money. you know, the right breakdown of the products to make the most money for you. But instead, in this one, we're gonna be purchasing products because we're the professor that's trying to put together 20 kits for an in-class simulation game, and you need all of these parts. You need 10 A's and 30 B's, etc. Okay. Problem is, they don't sell these parts individually. If they did, we wouldn't have to have this model. So, obviously, they don't sell these parts individually. Instead, they're in these toys that we have to disassemble and get the parts out of. And there's a store that has, there's 5 different toys, and there's a store that has 12 of each of those toys. And if you got a toy 1, for instance, it would have 3 A's, 5 B's, 2 C's, etc., like that, okay? So that's how you would know, the parts that you were getting out of it. And this is how much those toys cost. So our goal here is to try to not just go in and buy every toy they have, that's expensive, to strategically buy ones that will give us the parts that we need without us overbuying, okay, without us buying more things than we need. So it is a mix of products. It's the right mix of which products we're gonna purchase, but in order to not spend so terribly much money. So when we solve it, we'll answer the normal questions. What should we buy? How much is this gonna cost us? We'll even do a little calculation on what's the cost per kit. But we'll look at it then and see, what were the binding constraints, talk about that a little bit. But that will lead us into a couple of different ways of looking at this. Other questions that we might ask ourselves, like, what if we could get Toy 5 a whole lot cheaper? Would we buy all the Toy 5s that were available if we could? We'll talk about that one. What if we had a store that had more than 12 of these? What if it had 24? And how would that change our breakdown of the products that we were gonna buy, the toys that we're gonna buy? And then also, is there a minimum cost to number of kits to produce that would minimize cost? That really ought to be something else. But anyway, just looking at that, ought to be its own bullet point. But we'll do all of those questions. Then we'll move into another problem, which is a problem that comes out of the textbook. It's example 3.2, but I'm gonna add an extra little sensitivity analysis on the end of that problem. All right. This was the file that we were working on. It had the color and black and white t-shirt problem in there. So very small problem, easy to calculate. We did a one-way solver table where we were varying the number of minutes hours, that we converted to minutes that were available to us. And we talked about that. We then looked at both increasing hours available to us as well as the cash available to us. When you see these kinds of things, there's all kinds of questions that can be asked, but you need to make sure that you can answer the question, from the tables. If you want to use the tables, it's okay, but you still have to be able to set the charts up to reflect the answer that you're giving, okay? So you need to be able to do that. We talked about these one-way and two-way tables. But now, today, we're going to be working on example 2, which is the simulation kit, buy the different toys to get the parts out of it problem, okay? So all the things that you saw in the PowerPoint are up here in blue. 5 different toys, this is how much they cost, this is how many parts A, B, C that you would get out of these. The store has 12. You're planning on making 20 kits. In each kit, you're gonna have 10 A's, 30 B's, 20 C's. Okay, so all that information that was on the PowerPoint is up here in blue. What we are trying to do is buy the right amount of each toy that will keep us from overspending. We want to minimize that total cost of what we spend on these toys by how we break this down, and that's what Solver's going to do for us. That's exactly what Solver's going to do, is tell us this. But you can see the logical operators on here because you can see what are the logical constraints that you would have, and that's that you can't, the Solver solution can't tell you to buy more than 12 of each one because that's all the store has, is 12 of each one. And then also, you need to make sure that in this Solver solution, because if you were just trying to minimize costs, it would tell you to buy 0. 0 would be the minimum cost because you wouldn't be paying anything. But you have to have something in there that makes you buy them. In other words, you need to make sure you get all the parts that you need to be able to make the 20 different kits. Okay, Okay, so get enough parts to be able to make 20 different kits. Okay, all of that, of course, is minimizing the cost. That's a calculation we're gonna look at later. Well, it comes up, but it's going to use it later. Let's do the simplest calculation first. It's always more fun. Let's do the simplest calculation first. So if you went to C19, how would you calculate how many part A's you need? Or you can just tell me the number. How many part A's do you need?
200.
You need 200. How do you know? Because you're going to make 20 kits, but they each take 10 parts. So 10, however you want to put it in there. I don't care which direction you put that. That's your 10 times your 20. You've got to, you're going to make 20 kits. It takes 10 A's in each kit. So it's C20 times B19, but you do have to make sure that the B19 is an absolute reference if you want to copy this across. And I do. And these are like some super easy numbers to spot check. You know, they're really nice round numbers, so you can go, oh, okay, yeah, 600, 200, 400, yeah, that looks good.
What did you put in cell C19?
The C19 is C20 times B19. But you gotta make sure the B19 is an absolute reference if you're gonna copy it. So that's how many parts you need to make sure that you get. So the calculation for how many did you obtain is difficult. It's not that. You just have to think about this for a second. How would you know how many part A's you get? What's the solution is out there? You know what I mean? Because it's part of doing the solution. How many part A's? How would you calculate how many part A's you got? Yeah.
Some product of purchases in part A.
Yes. So if you think about it, here's what's happening. I'm going to go ahead and type some of this in here. I don't know what Excel's going to tell you to purchase here. Let's do round numbers because I can do round numbers way easier. Let's say it told you to purchase 10 of each of these. Well, then how many part A's did you get? 10 times 3, 30, plus 160 plus 210 plus nothing plus 100. You know, that's what you got. You got 10 of each of those quantities here. So I'll put in part A's, because that's how many you know are in each toy. Purchases, because you are going to be buying multiple of the different toys that are available to you. So it's some product of those two areas. Before I put the closed parenthesis on there, I was going to make that a absolute, oh, that doesn't do it after I did that one. Okay. I need an absolute reference on this one because I would like to copy this, and essentially what's going to happen is it's all the A's on first, the B parts, the C parts, the D parts, so that'll move, that won't, okay? And that's going to give me how many do I obtain. Okay, so let me just tell you real quick. These aren't super easy. Well, they're not any, there's zero. You have no idea if you did that formula right or you didn't do that formula right. So a really good plan at this point is to click over a little further over that row, click in the formula bar line, and look to see if things that you put absolute references in moved as you expected them to. Or in the case, didn't move as you expected it not to. Okay, but you know, did this go, did these things do what they were supposed to do? I think that's just good practice to get into checking stuff like that. All right, so that's gonna be one of the things you have to make sure of, that you get all the parts that you need. And then of course our objective cell is to make sure that we don't spend any more money than we need to, that we minimize this. So what's the formula or function that goes in here?
Some product, toy purchases in toy product.
Yeah. The sum product of, you know, how many of each of these did you purchase? How much did they each cost? This isn't going to be copied anywhere, so you don't have anything to worry about on relative and absolute addressing. But that's it. You know, again, if it told you to buy one of each of these, you'd be adding up 5, 18, 32, 23. Okay, so that's your total purchasing. And cost per kit, well, cost per kit's really easy, but it's a, I can't get it to do it. It's not a number that I'm going to use as the objective, even when we get to the point where we're looking at that, because of the main business division, but there's some other things that would be a problem. But the overall purchasing cost divided by the number of kids is gonna tell you what the cost per kid is. There are no numbers in there right now. I mean, 0 is a number, but anyway, because you don't have anything here, so you don't have values there. That's it, the model's set up, it's ready to go. In taking your time here, helps you for the next step, but at this point, you're ready to go into Solver. And in Solver, you have to think, what's my objective cell and what am I planning to do with it? So my objective cell is what?
Purchasing cost?
Yep, the total purchasing cost, and I want to
Minimize it.
minimize it. Okay, so I want to minimize B22. Minimize B22. Subject to changing what variables?
Total purchases?
How many of each? And that's what Excel's gonna tell us, how many of each of these to purchase. And then I'm going to have, well, that's the changing cells. Subject to the constraints, what's one of my constraints?
B10 to B14 less than 12.
Yeah, so the number that you purchased in there, the B10 to B14 has to be less than the 12 toys that they have in the store. Of course, you're gonna reference D10 to D14, because we're not gonna put hard-coded values in there, so you're definitely gonna make sure that, you have the flexibility to change those later. Okay, so B10 to B14, less than or equal to D10 to D14. What's another one? Yeah, so making sure that you get all the parts that you need. So that C17 to I17 has to be greater than or equal to, change that, greater than or equal to C19 to I19, the amount you need. Make sure that what you obtain is greater than or equal to what you need. Otherwise, you can't make 20 kids, and you have to be able to make all 20 of them. What's another constraint that you could add at this point? Yeah. Do you have to? No, but this is a small, easy problem. Just the purchases, I mean, let's go ahead and make that integer, because, they frown on you ripping the toys apart while you're standing in the store. So, anyway, so we wanna make sure that that would be integer. B10 to B14, integer value, okay. So here's what you have. You're minimizing B22 by changing B10 to B14, and your 3 constraints are, in order of the way that they're listed up there, don't have stop Excel from telling you to buy any more than 12, because that's all the store has. Make these integer, and then make sure you get as many parts as you will need for all 20 kids. It should have, this should be checked, this should be simplex LP. Solve it, and it finds a solution. Okay, that's the solution. I mean, at this point, what you know is grab your checkbook and go to the store and buy 1 toy 1, 7 twos, 12 for the next one, 12 for the next one, 4 for the next one. I mean, that's it, yeah.
I got it.
Yours didn't
They're not
solve
different
it
things.
that way?
Yeah. It didn't solve it that way, no. Do you maybe take a look at it or?
So, one of the things that you could do right now, if yours didn't solve correctly, is manually plug these numbers in and see if these are the same. Because then that might show some problems with your calculation. I mean, actually, if you plug these in manually, all those numbers ought to be the same, these numbers ought to be the same. And if something's not, then you have a calculation issue.
Right now it's.
Yeah. Okay, so the really straightforward thing is, these are how you go to the store and buy those toys in those quantities. That's gonna cost you $871. We don't have an IA in this class anymore, is that what you were looking for, Jimmy?
Yeah.
Oh, okay, I was gonna say he's not, good yet. So, it's gonna cost you $871, that's $43.55 a kit. And that's great, that's, straightforward, that answers questions on the PowerPoint. But then, if you're looking at it and you wanna think a little more about it, what's binding? What constraint or constraints is our binding. What's binding on here? So a binding constraint, I mean, when you're maximizing something like for rackets, you know, it stops you from making more. Here, it prevents you from saving more money, okay? It stops you from minimizing any further than you are. That may not help with the answer to this question at all, but when you look at this, what do you see as binding constraint or constraints? Yeah, toy 3 and toy 4. And they're the only things that you see on here when you're looking at it, that the value has exactly met what you had available to you. So you have 0 slack in this. In other words, you bought every toy that they had. You have 0 slack. That's binding. These 3 are not. None of these values are binding. That was close. Okay, but none of these values are binding. You ended up with, because of the breakdown of how many parts are the parts that are in the different toys, you ended up with more than you needed. Okay, but nonetheless, you know, those two, you get every bit of it. I will tell you right now, if you run an answer report, it's going to tell you the integer constraint is binding. It's always going to tell you that. But I'd prefer when I ask you the question about what constraints are binding that you actually give me one that's not an integer, but rather one of the normal physical constraints or something that goes with it. So these two are binding. What assumption you might make, okay, is that we would have purchased more toy 3s and toy 4s if the store had them. Okay? And that's okay to kind of think that, as long as you recognize that you really don't know that. Okay, you really, really, from this solution, do not know that. You might think you would have wanted to buy more, but there's no way to be sure of that unless you just test it out and see if you would have wanted to buy more or not. Okay? But before we get to that, we will test that in just a minute. But before we get to that, we'll look at sort of the next, you know, going in order of sort of the next thing that's on the PowerPoint, which says, basically is talking about a coupon website that would be available to the professor for Toy 5. But the bottom line of the question is, how cheap would Toy 5 need to be in order for us to buy all that they had? Because right now, we don't buy all that they have. It's $20, we don't buy all that they have, we buy 4 of the 12. That's it, okay, we don't buy them all. But how cheap would it need to be for us to buy all of them that they have? Okay, so here's the thing. When you're there the day of a test, on solvers and solver tables that are very explicit about, you know, laying it out, the question out exactly, parameters that go with it, you know, all that kind of stuff. But we won't do that always in class, because in class we're going to talk about things. We're going to, you know, see what we think we should do. But I also want to just talk about this, how you would structure this problem. Because what we're going to do is a sensitivity analysis using solver table, where what we have to think about is what input would we vary to get an output that would answer our question, okay? What input would we vary to get an output that would answer our question? And our question is, how cheap does Toy 5 need to be in order for us to buy all that they have, okay? What would the input that we were varying, what would that be? What would our input that we are varying, what would that be in that case? Question is, how cheap would Toy 5 have to be in order for us to buy them all?
The cost?
The cost of Toy 5. That's going to be the input that we vary, okay? So we'll vary this. Obviously, it has to be something less than, you know, $20, right? What's this? What would we use as our output that answers the question of whether or not we bought all that they had? What do we use as the output in that solver table? Well, yeah, exactly. The purchases of Toy 5. Because the thing that answers the question is that cell right there, okay? If it's got 12 in it, we bought them all. If it has anything less than 12, we didn't buy them all. Okay? That answers that question, okay? Whenever I have something that's gonna be output in solver table, I have a tendency to want to name that cell you don't have to do this, you really don't, okay? But a lot of naming things really just helps you in the interpretation later when you're looking at output. But I would name B14, I don't know, I named it 2 different things in different classes. I would name it quantity or purchases of toy for underscore toy for 5, 5, not 4. I'm looking at the 4 there and naming it toy for. Okay, quantity toy 5, purchases toy 5, toy 5 purchases, toy, I don't care what you name it exactly, but something that would let you know what that cell is. Okay, hit enter so it takes it. Does that make or break solver table? No, it doesn't. Okay, it just makes your solver table output easier to read. That's all it does. Okay, in this room and on some of your computers, every time you leave Excel, solver table goes away, and I don't know why it does it in this room, but it always does. So if I go to, I'm gonna have to turn solver table back on. If I go to File, Options, Add-ins, excuse me,
Questions?
File, Options, Add-ins, trying to get it to come up here. It looks like it's checked, yours may do the same thing. You have to uncheck it, click OK, and go right back into it again. I don't know why. File, Options, Add-ins, go right back into it, turn it back on, and this time it will show up. I don't know. I don't even know exactly why it does it like this in some places and other places it doesn't. I don't have any problem with this on my home computer, on my office computer. I don't have any problem. My laptop, I don't have any problem anywhere else. I have it in this room all the time, and I know some of you have it. Anyway, so when solver table is up, and we've already kind of talked about how we wanted to formulate solver table. When solver table's up, and we click on Run Solver Table, it always asks us if we have a model. Yes, we do. And if you think about this problem, we just said that there was just one thing that we were varying, okay? That we were varying the price of toy 5. So it is just a one-way table. And I had asked you, what's the input? And we said, well, the price of toy 5. B7 is the input. Price of toy 5. So the price of toy 5. Now, I asked you that question, we came up with that, we're gonna get to the rest of the stuff, but I don't have on here specific parameters like I would have if this was a test day, because I want us to talk about it. We need to set our range of what we want to vary it from minimum value up to a maximum value. Where do we wanna start? What do we want our minimum value to be?
1.
I think 1 is reasonable. You know why? Because we don't know. I mean, I think we're all pretty sure that if we were selling it for $1, we'd buy all that they have. I get that. But we really don't know where that cutoff is, where we would stop. I mean, so go ahead and say 1. 1 is fine. I mean, I think it's pretty safe to say we would buy them all at 1. But we don't know where the cutoff is, so how do we really know where to start, you know? So 1 is reasonable. And what would we want our maximum value to be? What would we take that up to, though?
20.
20. And it doesn't make any sense to go any higher than that. We could stop at 19 if we really wanted to, because basically we already know that at $20, we don't buy them all. Okay, I put 20 in because it's a nice round number, but I'm just saying you could put 19, I suppose, if you're thinking to yourself, I already know we don't buy them at 20, why would I go to 20? So 19, 20, I don't care, either one of those is fine. What could you put in as increments? You know, you start putting 10 cents, 25 cents, you're gonna get a really big table, and it may take a long time for this to run. So I'm just gonna put $1 increments. Okay, so I'm gonna have it vary the cost of, you know, the price of toy 5, B7, from 1 to 20 in increments of 1. And that's what I said, what cell gives you the answer that you're looking for? And the cell that gives us the answer that we're looking for, that's what we wanna see as output, is which one?
The purchases of toy 5.
B14, the purchases of toy 5. Now, that's the one that answers the question. It's just by looking at that we know whether we bought them all or we didn't buy them all. Okay. Varying B7, price of toy 5 from 1 to 20 in steps of 1. Looking at B14. And what we discover is that, I'll just highlight the brush.
What are the
this.
increments again?
What was that?
Increments?
One is the best to do. And I could do other numbers, because I didn't put anything specifically on the PowerPoint, but when, the toy is $10 or less, we buy all that they have. Once it hits $11, we still buy a lot, but we don't buy all that they have. And that actually took us all the way up to $19. That point where we crossed over and didn't, dropped all the way down to just buying 4 actually was the $20 mark. But the question said, when would we buy them? At $10 or less. Okay, if the toy was $10 less, we would buy every one they had in the store. Okay, let's go back over here with the regular, original prices. We find out there's a store that actually has 24 available. They're clear across town from each other, so we're not gonna go to both stores. We're just gonna go to the store that has more now. So all we have to do is just update that constraint value. That's all. Well, I mean, not all, we have to solve right after it, but we don't, there's nothing else about the model that we're changing. We're just saying, oh wow, there's a store that has 24. Yay, okay, let's find out now what our overall cost will be and what we should buy and all that stuff. We go straight back into Solver, and because all we did was change a constraint value, nothing about this needs to be changed. Okay, we don't change anything about that, we just solve again. That's it. With that new 24 toys for each, we just solve with that in there. And then, yes.
Whenever you run Solver, I remember last class you showed us like a report that Solver itself gives you other than
Yes.
Solver table.
Yeah.
How do you get that again?
When you have just, well, I'll show you on this one, but when you have just run it, just immediately after you say solve, that's when you get some reports in here. I would have thought I would have had more than this, but anyway, the answer report there, when you click OK on it, it opens up a new little answer report thing. It has, there's another report that I'm looking for. Oh well, this is the answer report that you get that tells you what's binding, what's not binding. There's another thing we can do to get shadow prices and all kinds of other stuff, but we're not covering that in this class, but there is another thing you can do to get that, which would help you to figure out whether or not you really wanted to buy more of this or didn't want to buy more of this. Okay, here's maybe you expected it, maybe you didn't expect it, I don't know. But turns out we didn't really want to buy any more toy 3s. That 12 was all we would buy, even if there had been more. That we would buy one more toy 4, but that's all. So it wasn't like, oh, that was, we don't know. I mean, binding is binding. It was binding, that's all we could tell. We didn't have any idea what, from that we wanted to do. But it wasn't so holding us back from saving money. I mean, yes, a little bit. We went from $871 to $864. By having another toy 4 available to us, we saved $7. That was it. Okay. We don't know that from the original solution without running some other things or just testing it out like we just did. Okay. But then it asks the question, and I should separate this out as a different bullet on the bullet point because it's kind of buried at the end of the question about 24, but it says, is there a number of kits to produce that would minimize the cost per kit? Okay, I want you to listen to this. It says, is there a number of kits to produce that would minimize the cost per kit? That might make you think that you want to shift this to where this is your goal cell and you minimize it by changing that one also. You still have to change those. By changing that also, and that is not what you want to do in this situation. It won't work, and the model, anyway, it won't work. And that cell is dividing, and that's nonlinear, but it's not just the nonlinearity. There are a lot of reasons it doesn't work. So that isn't what we want to do. We want to stick with the model the way the model is, and find a way to use a sensitivity analysis, aka solver table for us, to figure out if there is this minimum, this number of kits that would produce the lowest cost per kit. okay? And so, if what we're trying to do, and again, with a sensitivity analysis solver table, not reworking the model, okay? If what we're trying to do is figure out if there's a number of kits to produce that would minimize our total cost, what would our input changing cell be? What we're trying, the question we're trying to ask is, what's the number of kits that would give us the lowest cost per kit? And what is our input? The number of kits. Okay, that's the thing that we're gonna be changing right there, the number of kits. Is there a number of kits? You know, I'm gonna change this in order to arrive at the lowest possible cost per kit. So my output cell then is gonna be what?
Cost per kit.
Cost per kit, yeah. Since that's gonna be my output cell, I'm gonna name it. Put this up here. Cost underscore per underscore kit. Something like that. Again, just because I just want you to get in the habit of naming these output cells, it'll help you so much, especially on two-way solver tables. All right, so let's go back to solver table. That's what we're gonna run an analysis on that. Yes, we're on a sheet that has the model. There's only one thing we're changing, and that's the number of kits, so it's a one-way table. So it's great that this dialog box retains the information that you had in there from your previous solver table that you did, because that way, if you'd made just a small mistake, you'd go back into it, you could rerun it, you know, if it was a mistake on the worksheet, or you could fix the little thing you need to fix. It's great because our graders need to see it to be able to grade your exams, the whole works. But unlike Solver, it doesn't have a reset button. So whenever we want to do a completely new solver table, we have to clear everything out ourselves, because there's not a reset button on this like you would have on Solver. So we just have to clear it all. No choice. That's just what we have to do. So if our solver table is something completely different, you know, that we're wanting to do, the easiest thing is just to get rid of the values that are in there right now and start over. It's just easier. Okay, and we just went through this. We just talked about this. Our input cell would be the number of kits, if what we're trying to figure out is if there's a number of kits that would give us the lowest possible cost per kit. So B19, number of kits, okay. I'm not really suggesting that you should just logically know what we should do with this. I mean, really honestly, we don't know. We don't know at what level, you know, the cost per kit will be minimized. So I'm just gonna have us take it from 1 to 50 in steps of 1. And again, on the test, I will tell you exact ranges of things to use, so you won't be guessing at it then. I just want class, you know. And then we talked about that the output cell would be the cost per kit, which is B23. So we would be varying B19, the number of kits, from 1 to 50 in steps of 1, and then looking at B23, the cost per kit is our output cell. And when we click OK, takes it a second, but it eventually gets there. So here's the thing, it is pretty expensive if you're only trying to make 1 or 2 kits. And then it starts coming down from there, and then it kind of levels off a lot. I don't want to trust my own, you know, eyes to find which one is the lowest one. So, but before I even get to that, this is one of the interesting things that comes from that output. And that's to discover that. And remember, the last time we ran the model, we had 24 toys of each one available to us. But even with 24 of each of these toys available to us, that would not give us enough parts to make more than 46 kits. So if we needed to make more than 46, we'd have to go somewhere else and buy more toys. But at present, what we know is that with 24 of each toy, we cannot make more than 46. And that's an important piece of information to have, to know. Okay, so but that's why that's saying that's not feasible, we wouldn't have enough. So like I said, I don't even wanna rely on my eyes to figure out what the minimum value in that list is. So I'm just gonna find the minimum cost in this list from 1 to 46 kids. Turns out the lowest cost is $42.95. Okay, again, could I scan through and find it? Oh, sure, I probably could, but it really is just as easy just to do a match, and just match that $42.95 in this range. And I know that it's an exact match, because I just pulled the number out of there, okay? So I know it's an exact match, so just match that number in the range, and you'll find out it's 37. Or scan down the list and find it, I don't care. I'm just saying, that's a quick way to get that information to me and know that it's accurate, is that I find the minimum, it happens to be at 37 kids. Okay, right here at 37 kids, that's when I reach my lowest cost per kid. That doesn't mean this, costs less than making 20 kids, oh, no way, because you're buying way more stuff. Your costs increase with every kid that you're making. Your cost per kid is what we were looking at, not your overall costs. Your overall costs are gonna go up the entire time you are making more and more and more kids, okay? The costs are gonna keep going up. This question was specifically referring to the cost per kit. When was it at its lowest point? And it said its lowest point when you make 37 kids. Right, okay, that's the end of the toy simulation example. And we solved it just in a straightforward way, but we made modifications to it as like there's more toys available, or, how cheap would toy 5 have to be in order for us to buy them all? What was the last one? We just did it. What's the number of kits that would make this, the cost per kit as low as possible? So these are great to look back at, because it helps us to think and formulate what the solver table ought to have in it, input, output, to answer the question. But don't get worried, because I will be very explicit in exams on exactly what you're supposed to do in ranges and everything, so. Okay, well then, if everybody's okay with this one, we'll shift gears. Yes?
It's just a question, but if solver tables, when you're not working well on your Mac or parallels, it's a good idea to go to the library and check out one of the laptops and they have, do they have solver table?
I doubt they would have solver table, and you wouldn't be able to load your own stuff onto it, so they would have solver, but not solver table. Yeah, we have them here, okay, so in the lab up here, to the left, if you're looking at Starbucks, to the left of Starbucks, we have it there.
Okay.
So we have it. But if are you running Parallels or Boot Camp?
I am running parallels, yeah, but for some reason when I put the numbers, it's not coming out feasible part.
It should be,
Okay.
okay, it should be, so that's probably a mistake in a different
Okay.
way, but we'll do that. Okay, example 3.2 is the one that is also in the textbook, so one good thing about that is that you will be able to, especially on these more tedious formulas, in this one part of this, you'll be able to look back at the textbook and be able to see everything and the explanation that goes with it, the whole works. But let me give you the Reader's Digest version of what this says. We make 8 different models of computers. Everything you see up here in blue, of course, is a given number. We know that what we're gonna sell them for. We then have some costs, like the component material costs. We have labor that goes into it, that there are a certain number of hours and certain rates, okay? So we'll have to work on that, but all that information is given to us. But we also know that there is a, kind of what we've predicted to be a maximum demand, so therefore we think of maximum sales. And under the assumptions of this model, we don't wanna make more than we think we could sell, okay? That's our choice, we don't wanna make more than we think we could sell. So we've got those numbers here, but we also have constraints on the labor hours that are available to us, and we can't use more of that than we have. But here's what you have to know about this problem, and of course it would be in a textbook and you can go back and look at it. But when we manufacture these 8 different computers, they all get assembled, okay? They all get assembled. But then for testing, they either go down line 1 or line 2, not both, okay? So they either go down line 1 or line 2. There's no requirement that certain computers go down certain lines. That's not. It's just, you know, it's open, I guess, whatever. But we're gonna make an exact plan for this, but they go down one or the other, but not both of the lines for testing, okay? So you need to know that for the calculations that we're about to make. What we're gonna have Excel do for us, with all our calculations and everything, but is to tell us exactly the breakdown, the product mix of these 8 different computers, and even beyond that, whether they should be tested on line 1 or line 2. Okay? Now, when we were doing the color and black and white t-shirts, I said, if you had enough time, you could play with those 2 numbers and come up with what the maximum profit was. I mean, it'd take you a little while. Nobody really wanted to do that. I'm just saying it was like a doable thing. This, not so much so. Okay, you got 16 different boxes here, the 8 products, the 2 lines. You are not doing this unless you really have nothing left to do with your time for a very, very long time. You're not gonna come up with what's the best solution here. This is when, you know, the miles get bigger that you begin to need something, you know, like Excel for sure. Okay. But that is what we're asking Excel to do, is to give us that breakdown. Okay. But let's just start at the top, work our way down. In cell B14, we're gonna calculate what's the unit margin of a Model 1 tested on line 1. What's the unit margin of a Model 1 tested on line 1? Where would we start? What would we start with?
Selling price.
Selling price. Because unit margin is the selling price minus the unit cost. And selling price is basically the revenue of a single unit, okay? So B13, and we now start to subtract out the different costs. What could we put in next? Yeah, I always put the component parts in there next because it's one of the easier ones to do. And then we would subtract out what else?
Cost for assembly.
The cost for assembly. And the cost for assembly is 4 hours at a rate of $11 an hour, okay? So we take the selling price, we subtract out the component part cost, and then the assembly cost is going to be, you know, 4 hours at $11 an hour, and then we would subtract what else?
Testing?
The testing on line 1, which would be the 1.5 hours you see in B10 times $19 an hour. Good? Okay, so you don't put testing on line 2 into this formula because this formula is, remember, they don't do both. So this is just the formula for the unit margin if you were tested on line 1. The selling price minus the component prices, you know, then the assembly, which is the hours times the rate, and then the testing on line 1, which is the hours times the rate. Okay. And that's all good. That's all good. Just real quick. I'm putting decimal places in there, I'll make it more accurate. $127.50, great. Okay. The thing is, I'm going to want to copy this across this row and then down to the next row. And that's gonna make this messier, for sure. But I'm gonna click up here in the formula bar line just so I can kind of see all the things that are referenced in this formula, and I'm just gonna take it one reference at a time. Okay, B13 is a reference to selling price. What do I want to do there with respect to absolute values?
Put the dollar sign between the B and the 13?
Right, in front of the 13. Because I want the column to change, but not the row when it moves down, okay? What about the B12, which is a reference to the component part?
Same thing.
Same thing, the dollar sign in front of the 12. What about the B9, which is a reference to the labor hours for assembly?
Same thing.
Same thing, just in front of the 9. What about the B3, which is a reference up here to the labor rate for assembly?
On all of the, both of them.
All of it, yep. What about the B10, which is right here, the reference to labor hours for testing on line 1?
In front of the column.
Line in front of the column?
In front of the 10.
You don't want it to be able to move. Do you want it in front of the 10? Do you?
Mm-hmm.
So look at it look at how it's set up, line 1, line 2. So we're gonna be copying this across. We definitely don't want it in front of the B of the B10. But then we're gonna copy it down. We do actually want it to move to row 2. So you don't put anything on the B10. Okay, the B10 should not have anything. Okay, what about the B4, which is a reference right here to the labor rate for testing on line 1?
Front of the B.
You can, I mean, if you put it in front of the 10 just by habit, it's fine, right? On in front of the B10. Is that okay?
It's not okay. It's
Oh,
not
like
okay.
the dollar sign? Oh.
Yeah. It would.
Yeah, because it wouldn't go down.
Okay, I'm sorry, what, are you talking about the B4 one?
No, I was just, yeah, the before one I was just gonna say if it would be in front of the B.
It's just in front of the B. Because the 4 part of it is like we were just talking about, shifting from line 1 to line 2. You know, so that moving down is good, because we're shifting from line 1 to line 2. This one, the B, is because, you know, you're over here, you don't want these things moving across. Okay, that's the way it's supposed to be. On the B13, B12, B9, all in front of the row number. B3 is everything, B10 is nothing, and on the B4, it's just in front of the B. Now, do we know that we're right? Well, y'all have done this a lot of times, so I'm pretty sure, but, you know, I'm always gonna check stuff. I'm gonna copy this across this row, I'm gonna copy this down, I'm gonna move over to a cell that's further down that first row, and I'm gonna click on it and let everything show up and see if it makes sense. I mean, kind of, you sort of can tell, obviously things could be all scrambled around, but at least you can tell. It's not referencing anything that has to do with line 2, we're testing line 2. I would move to another row, another column. I'm on the line 2 row now. It's not referencing anything for line 1. Testing line 1. Okay. Let me just show you a real easy one. But if on that B3, for a reason, we had left the dollar sign off of the, in front of the B3. If we had, and we copied it, and copied it again, these numbers would not trigger anything in our minds that anything was wrong. It just wouldn't. I mean, we wouldn't look at that and say, oh, there's something wrong with that. But when I click on this and click in the formula bar line, and I see something like that, boom, immediately I know I didn't do one of my absolute references correctly. And of course, it's the one that goes with that row, which means it was the one for B3 that should have been over here. So that is really, it's really a good way to fix, to notice problems. Can you notice all problems that way? Probably not, but it helps a little. I mean, there are some that would be very noticeable, and you would be able to go in and say, oh, wow, yeah, I messed up on that. I messed up on that absolute reference, and it should have been, you know, in front of the B, so that didn't happen. And here's what I think about that. Your models, not so much on this test, but on the second test, maybe like a really long one. And you want to catch things as quickly as you can. Because if you don't notice it, and you go all the way through it, you don't notice it, and you solve, and you don't notice it, well, then you just go on and there's been a mistake. But if you solve and all of a sudden there's an error, and you're like, oh my gosh, something's wrong. The thing about that is you don't really know if the error is in the way you were setting up Solver, or if the error was back here on the spreadsheet before you ever got into Solver. And so then you kind of have to backtrack everything again. And I'm not saying that might not happen anyway, but you cut down your chances of that happening if on every line that you go through, you're just more meticulously careful about it. And you do that kind of a checking thing. And here's why. That's when your mind is on that, your mind is on this here. Now you can go and do the rest of the stuff and come back and it's like, oh gosh, I have to think about this again. You know, you don't wanna have to do that. If each line, you checked each line as you went, your mind is on it, your mind is freshly on that, you can see when something is wrong, you just, the more careful you are, the better chance you have in the long run of things working out, you know, well. So I'll just mention that. But anyway, that is the calculation of those. Is it a little messy? Yeah, a little bit, okay, a little bit, but it's not horrible. It's just, you know, there were so many mixed addresses in there that it wasn't gonna help you to name cells. I mean, there's just too much in there that you had to put in correctly. All right, so now, let's look at B21 and calculate. You have instructions to go here, but you can also see it's our next box that requires a calculation. And B21, how do you calculate the total computers produced of Model 1?
Sum total.
Yeah, just
Sum.
some these. Yeah, whatever went down line 1, whatever went down line 2 together, that makes up how many computers you made of Model 1. And that would be true all the way across. And is that a super simple formula that didn't need real absolute addressing? Yeah, it is. But you still might want to get in the habit of clicking over here, clicking here, looking at it, and making sure that it's right. And yes, I know it was a super simple one, and you might not even think you need to do that, but it's one of those things like get in the habit of doing it each time. Okay. So another thing that you might have to do, and you might have to do the day of the test, is fill in logical operators. But you do need to know, you do need to have an understanding of this, because when we look at demand, we are sometimes saying we want to meet demand, in which case we're saying we want to produce greater than or equal to what the demand is. We want to make sure we always have enough, you know, to supply all the demand that we have. There are other times where we do something like this problem, where we say we believe there's this maximum demand that we don't want to exceed, like we don't want to make any more than we believe we'll sell. And that's kind of the way it is in here. We have a maximum sales here. We don't want to exceed that, so the logical operator we need to put in here is what?
Greater than or
Okay, we want to make sure that we don't produce more than we could sell.
less than or equal.
Less than or equal to. And does that make or break the model itself? No, it's documentation on the worksheet for you. That's all it is. But it does make it easier for you when you go to put these into your solver if those are all on the sheet. And if it's in a problem, I'm going to ask you to do it. There'll be points associated with it. But anyway, so we'd have to put logical operators in. And while we're on logical operators, what would we put here? Because you know you always make a calculation of the amount of a resource you use to make sure you don't use more than is available to you. So we should put what logical operator there?
Less than or equal to.
Yeah, less than or equal to again. Okay. The hours used for assembly. How do I calculate the hours used for assembly? Okay, so you're right, it's the sum product. Okay, of what now?
The computers produced
Yeah, it is actually computers produced, and what else?
labor hour.
For assembly. Okay. Okay, so it is the sum product of, so in other words, here's the thing. All the computers go through the assembly process, so that's why you're using this row that has the total, you know, total computers produced, because they all go through assembly. For every one of these, we produced 4 hours, plus however many Model 2s times 5 hours, plus how many Model 3s times, you know, so that's how many assembly hours we used. Okay. How about testing on line 1 hours? What's that gonna be?
Same thing with test on line 1.
Yeah, it's gonna be a sum product also, but it'll be the hours associated with testing on line 1 and the number of units that were tested on line 1. Because this only applies to the testing on line 1 stuff. So again, for everyone that goes down line 1, it's a model 1, it's an hour and a half. It's model 2, it's 2 hours, model 3. And I'm lazy, so it actually will work for me to copy this to the next row, because that just takes it from line 1 to line 2, right? And I'll double check that, but that just took it straight from line 1 to line 2, just down 1 row. Okay, the hours associated with testing on line 2, the number of units tested on line 2. So that was my fast way to get that in there. If you wanna just retype the whole thing, that's okay. That's not a problem. Okay. And then to eventually get to the profit here, and there were a lot of things, shortcuts we could have taken to this, but in the book, the structure of the problem is such that they did the profit for each model on each line. Then they added them, then they added them again. Okay, all in the sum product, but that's okay. So what's the profit of model 1s overall, for all the model 1s tested on line 1? What's the profit? The unit margin for those tested on line 1,
Number of tests.
multiplied by the number of them that were tested on line 1. Yeah, that's it, B14 times B19. And here's the thing about this. You don't really wanna copy this, and I wanna copy it across the row to here, okay? And then down to the next row. Well, the shape of this is just like the shape of this, which is just like the shape of that. And everything is positioned at the exact same place. We don't need any absolute references on this. We actually can just copy it. Now, are we gonna check that? Of course. Okay, but we can just copy it across to model 8, down to the next row. Should we check it? Yeah, we should check it. Let's look at model 7 on line 1. Line 1, model 7, good, okay. Let's look at model 5 on line 2. Line 2, model 5, good. Anyway, but we didn't need absolute references on that. And then, this is my fast way of getting the totals in here. If you go to J31 and auto sum, it'll give you what you were wanting there. Go to J32, auto sum, picks up that whole row. J33, auto sum, there's nothing in the row, so it picks up the 2 things above, boom. So just like that, auto sum, enter, auto sum, enter, auto sum, and enter, you're like, I've got them in there really fast. Just say, you can put yours, you can put them in there any way you want to, but that's, you know. Now, again, just so you know, we could have gotten this number right here with a sum product of these 2 ranges. Okay, so we could have gotten it that way. We didn't, that's not the way they structured the model, so we drug it out. All right, so everybody's got all this in, everything's ready now at this point for us to solve it. We go into solver. Okay. Our objective cell is this overall net profit that you see down here in J33, and we're wanting to maximize profit, of course. So J33, maximize it. We do that by changing those 16 cells, those cells that tell us how to break down which models to make, but not only which models to make, but which line to test them on, okay? So our changing cells are B19 to I20. What's one of our constraints?
The total number of computers.
Total number of computers produced needs to be,
Less than or equal.
yeah, to the maximum sales. So B21 to I21 should be less than or equal to B23 to I23. So not exceed, in our production, we should not exceed what we believe would be the maximum we could sell. What's another constraint?
Hours.
Yeah, make sure for these 3 different labor hours that we are calculating, assembly, testing on 1, testing on 2, that as B26 to B28 is less than or equal to how many hours are available to us for assembly, testing on 1, testing on 2. So B26 to 28, less than or equal to D26 to 28. And we could go ahead and add a constraint that does what?
Make the profit or anything.
Yeah, make the products, how many we make integer. And since this is a book problem, I have a feeling they made it where that wouldn't even matter, that they worked it all out. I don't know. I'd have to look back and see for sure, because I don't like doing the integer thing, but so, in order of the way you see the constraints up here, make these integer, make sure you don't produce more than you feel like you could sell, and make sure you don't use more labor hours than you have available to you. This, I don't know if yours is on this, or if I just saved my file in some weird way, but that should say Simplex LP. All of them that we do in the first 2 tests are Simplex LP.
Wait,
I don't know how that got on.
26. B26 to B20.
So J33 we're maximizing by changing B19 to I20, subject to those 3 constraints. Simplex LP, solve it, and there's a decent, good solution to this all. We, I didn't ask in the other classes, but we have binding constraints here for assembly hours and testing on line 1, so we don't make any more computers than you see here because we were running out of assembly hours and testing hours. We make a profit of $615,813. We make all possible Model 1s we could make, Model 6s, Model 7s, we make some Model 4s, but weirdly enough, we don't make half of the computers that we say we make. You know, we have these 8 different models that we make, and we don't even make half of them. So here's the thing about that. What you have to understand when you run a solver model is that this is a mathematical model, and it did exactly what you asked it to do. It gave you the breakdown of how you ought to produce these to get the highest possible profit that you could get. But what you have to understand at the end of any one of these models that it's ultimately you're still the decision maker. This is just a tool that you're using. So when you look at that and you see this result, it might dawn on you that, oh my, I don't want us to not make half of our computers, because if we don't make half of our computers, we don't have the selection that our consumer is looking for, and therefore they turn to somebody else for something like a Model 2 or a Model 3, and now they're a lifelong customer of them and not us anymore, and we might be sacrificing long-term market share for short-term profit, okay? And so we really have to ultimately understand that this is a tool that we're the decision maker. And if we see something like that and we say, this isn't a good idea, you know, and maybe it is a good idea, maybe we're just trying to cut out our not as high producers, I don't know, you're the decision maker. But you need to recognize that sometimes you get results from solver models that later you say to yourself, I should have made sure that we produced at least some minimum number of each one of these. And I'm gonna do that right at the end. And I'm going to do that and just go back and show you something. But before that, I'm going to real quick do the solver table question that's on the PowerPoint, which is to vary the number of assembly hours. Like right now, we're maxing out. We have binding constraint here. There's 20,000. But we're just going to do like less, more. How would that impact the computer breakdown of the computers that we make, as well as how much profit we make? But I want to use this opportunity to show you something else. I always tell you that for the output to name the cells, and that's a really good idea. So I would name J33. You can't name it profit because that was on our color black and white sheet already. So call it total underscore profit. But the other thing I'm going to want to see in the output are how many of the 8 different computers I'm making. So I am picking up a range that has those 8 computers as well as the text that's to the left of it. Okay? And I'm gonna go in on the formulas ribbon to where it says create from selection. And I'm going to let it create a name for those cells based on the text that's in the left column. Okay. And I'm gonna click OK. Right, you're gonna think absolutely nothing happened, and you're really not gonna know that anything happened until later when I'm looking at the output of solver table, but you'll see it in just a second. So when I go into solver table, to run solver table to do the one that's on the PowerPoint, I say yes. It is just having me, if you read it, it's just having me vary the assembly hours, so it's just a one-way. Real straightforward, all the parameters are on there. My input cell is D26. The assembly hours available. It tells me exactly what to do on the PowerPoint, go from 18,000 to 25,000 in increments of 1,000. So D26, assembly hours available, vary them from 18 to 25,000 in 10,000 or 1,000 increments. And then look at, and then here was why I named all these things. I want to see the breakdown of how the computers that are produced, that's B21 to I21, hold the control key. I also want to see J33. Okay. So I want to see all of that as output, that's why I named them. Right, PowerPoint, D26 the input, parameters from the PowerPoint, and I want to see the computers that are produced as well as the profit, total profit. So here's the thing. Even when I vary the labor hours available to me, I make as many possible computer 1s and 6s as I can. When I have more hours, I begin to ramp up production of Model 4, and down here begin to go down on Model 7, while at the same time I'm introducing Model 3. I never make 2s, 5s, and 8s, which is probably not a good idea, but, well, I don't know if it's a good idea or not. Maybe I'm trying to get rid of my low profit margin ones. I don't know, okay? But anyway, that's just a follow-up follow-up solver table to the one that was already in there. But I do want to show you this. If in that original model we said, man, it doesn't make a lot of sense for us to not make half of our models. You can always, after the fact, go back in, and I'm just doing this super fast. Let's say I want to have at least, not 1,000, at least a minimum of, a minimum of 100 units of each type. So I don't want to have entire models that we don't even make. I want to at least have them, I saw the output, we're only making half of them, bad idea for market share reasons. I want to at least make them. Then all you just do is go back into your solver and you add in this new constraint. And this new constraint would say that the number that you produce of each of those models has to be greater than or equal to 100. Well, I put 100 in a cell and reference that. Because I don't want it to happen that we have entire models that we just don't make at all. Okay? So I click OK, I solve it. It still solves, everything's still good, but my profit is lower. It went from 615, 800 something to 610. Okay, I get that, and here's why. When you tighten and loosen constraint values, or add new constraints or drop constraints, it has an impact on your objective cell, your objective function. Because here's what happens. If you tighten constraints or add constraints, you're going to negatively impact, could stay the same, but you typically negatively impact your objective function, which means if it's a profit maximization thing, you'll have a lower profit level because you're imposing this constraint it didn't want to originally do. It didn't want to make 100 of each one of them. It wanted to only make 4 of the 8 computers. But once you make it do that, it's going to tighten your constraint, add a constraint, it makes it, it lowers your objective, if there's a maximization, it lowers the objective function. Okay. When we loosened a constraint on the toy simulation kit thing, and we said, oh no, now the store has 24, not just 12, that actually, a loosening of a constraint or a deletion of a constraint, this was a loosening of a constraint, actually has a positive impact on your objective function. Our costs went down. That's a positive cost for the costs to go down. And so that's what's gonna happen. Can things stay the same? Yes, they can, okay? But if you tighten constraints, it can never get better. If you loosen constraints, it can never get worse, okay? So anyway, that's what we're looking at. But this is the end of the material that's on the test on Friday. Okay, so you have everything you need. You have data tables, you have all the information that comes from chapters 2 and 3, which we have a lot of examples for, and you have textbook examples for. It's everything since quiz 2. But when we come in here on Thursday to review, if you haven't, you want to make sure you look over it, because if you don't look over it, you don't really know which things do you have questions over. So make sure you've looked at it before Thursday, which probably is just a really good idea if you have a test on Friday anyway, but make sure you look over it before Thursday so that you will have questions to ask.
What's typically the average for